Hello again, AP Calculus BC students. Mr. Record here from Avon High School, and we're going to look at our example number 9, which is our 9th video in this very robust topic, 9.7, which is typically all about calculus and polar equations. But this time in this video, I promise we're going to really clean things up. And we're actually going to be looking at some true calculus. In fact, we're going to be looking at the slope of a tangent line drawn to a polar curve, and then may even investigate where a vertical tangent line may occur. But first, I want to kind of share some preliminary information about slopes and tangent lines. And it says here, well, we'll just kind of read this together. To find the slope of a tangent line to a polar graph, consider a differentiable function defined by r equal f of theta. Well, of course, that was what we're going to do. That's what a polar graph looks like. R equals something with a theta in it. But to find the slope in polar form, we're going to have to use parametric equations because we're going to have to figure out a way to slowly meander this to a dy dx setup, because that's what slope is. Rise over run, change in y's over change in x's. We got to get x's and y's in here some way. And of course, the best way to do that is to use our good friend r equal cosine of theta. Now remember, if r is f of theta, then we have the same expression there. Likewise for the sine, for the y, r equals sine of theta, f of theta is sine of theta. Now, of course, we're going to rely on our good friend, the fact that dy dx is dy d theta over dx d theta. You don't have to think back very far to when you were doing this with parametric. Replace theta with t, and that's exactly what you have. Now, obviously, we're going to have a bit of a product rule on our hands, and as I can see that's going to come about when we actually take those derivatives, but that's okay. We all know how to do the product rule. And when it all comes down to it, guys, this is the form that we get, but I think it's quite silly to worry about memorizing that. I've never worried about memorizing that. I never taught it that way. We just simply set up our f of theta cosine, f of theta sine, take the product rules, and assemble this correctly. Now, word of caution. Yes, using the formula above, you have to understand some observations. If you're looking for horizontal tangent lines, which is an awesome connection, horizontal tangent lines will occur when the derivative of the numerator, dy d theta, is 0. When you're looking for vertical tangent lines, that's going to occur when the denominator is equal to 0. However, there's some extra caveats for both of these conditions, and that is provided that they're both not equal to 0, and I mean both by the top and the bottom. They're both not simultaneously equal to 0, because if that were the case, you can make no conclusions about tangent lines, and that's really important. So with that, let's take a look at our official example number 9. So the very first thing that we're going to do with this is to read it. It says a heart examination. Consider the cardioid, get it? Cardioid, heart examination, described by the polar equation r equal 1 plus sine of theta. So before we can really get going with this, we need to rewrite this in its form for x and y. So x, as we all know, is just simply r, 1 plus sine theta in this case, times the cosine. There we have it, all set to go. Y, on the other hand, is r, 1 plus sine theta, multiplied by the sine of theta. Now, at this point, it's really up to you if you want to distribute the cosine in and distribute the sine in. Some students like to do that. I'm going to go ahead and leave them separate because I can still go ahead and take a derivative fairly easily with the product rule. So remember that finding the slope of the tangent line is all about finding dy over dx. That has not changed since the very beginning days of Calculus 1. But now that we're in this world of polar, we're going to have to think of dy dx as dy d theta over dx d theta. When I say dy d theta, I mean the derivative of y with respect to theta all over the derivative of x with respect to theta. So, product rule, here we come. I might need a pretty long fraction bar here, guys, so I'm going to draw that in. And then please always remember, even though you typically write the x equal before the y equal. That's kind of how our minds think. It's this y equation that has to go in the numerator. The y derivative equation or derivative expression goes in that numerator. So be really mindful of that. So the derivative of 1 plus sine is cosine. Multiply by sine. Add to that 1 plus sine. And then we multiply that by the derivative of sine, which is cosine. And so there is your numerator. Do the same thing with this denominator. Derivative of 1 plus sine is cosine. Multiply that by cosine. Now, normally I think we would subtract. Yeah, that's fine. Or normally we would add. I got a feeling that that plus sign is probably going to change, but you know what? We can just take care of it down here. Yep, I was right. The derivative of this cosine is indeed negative sine. So it's very likely in the next step I might change that plus to be a minus. Now what we're instructed to do, especially if you want to show good notation, and we all would like to show good notation, is we're going to evaluate this derivative specifically when theta is pi over 3, which is just a lot of plugging in, basically. So we're going to replace all of these theta values with pi over 3. And if you weren't sure what the heck's going on with pi over 3, well, I'm going to show you right over here. If this angle is our pi over 3, we know that this is to be a 30, 60, 90 triangle, this up here being our little 30-degree angle. That's going to make the opposite side 1. This side here would be a square root of 3, and the hypotenuse would be a 2. Now, remember, this is our home base here, pi over 3. So the cosine of that angle would be 1/2. So I lead off with a 1/2. And then I multiply that by the sine of that angle, which is root 3, square root 3 over 2. And then to that, I will add 1 plus the square root of 3 over 2. And then that would be multiplied by the cosine of that angle, which is 1/2. Pretty much doing the same thing for the denominator. Cosine of pi over 3 is 1/2. Multiply it by itself. You're at a 1/4 right now. Add that to 1 plus root 3 over 2 yet again. And then we're going to multiply that by negative, and the sign would be root 3 over 2 yet again. Now I know that this is a pretty messy expression. And a lot of times in my class when I'm teaching this, I would just stop here and say, guys, we're okay. I noticed that we're not going to really do anything with this, like write it in equation of a tangent line, which would kind of motivate us to want to kind of simplify that a bit. But I tell you what, I'm going to go ahead and just spend a moment to try to get this into its lowest terms. We're going to have to distribute this 1/2, and doing so would give us something like this, I suppose, in the numerator. And then for the denominator, I have a 1/4. I'm going to distribute negative root 3 over 2. This is going to give me negative root 3 over 2 minus 3/4. If we continue to simplify, I am going to multiply the top through by a 4. What this does is essentially gives me root 3 plus 2 plus root 3. And if I multiply the bottom by 4, I have 1 minus 2 root 3 minus 3. And when all is said and done, 2 square root of 3 plus 2 is on top. Negative 2 minus 2 square root of 3 on bottom. And if you really look at this very closely, this reduces to negative 1, which is pretty nice and easy to work with. So I'm going to show you a visual representation of this now, and we're going to see truly does the slope of this particular tangent line at that place look like it could have a value of negative 1. Let's take a look. So here we are. I have taken it upon myself to sketch the graph of 1 plus sine theta, and that's what he looks like. He is a true live cardioid, kind of situated there up above the pole. And what I'm going to do next, because I'm using the TI Inspire, I can go into this menu geometry option, and I can actually affix a tangent line to a polar curve. Now I got to be careful because I've made this monstrosity by putting a lot of circles and lines in here. So I want to make sure I am selecting the polar curve. I would agree that that is the polar curve. Boom, there is my tangent line. Now if I can position this over here where he's at the pi over 3 spoke, which might be easier said than done here, but I'm going to do my best to position it. Doing my best, you guys, and I don't know if I can, right there. I got very lucky because if you take a look at this equation here, it has that slope of -1. Maybe if I drag it out, you can see it. And then I can always extend these if that helps you really visualize that this truly is a tangent line drawn to this curve here at the spoke, pi over 3, and you can easily see that it's got a slope of -1. Let's tackle our part B now. Now our part B is going to keep us occupied here for a little bit because it's asking us to find the points on the cardioid where the tangent line is horizontal or vertical. And so that does imply that both of them are in play here for this particular problem. So I'm going to go ahead and jot down our headings, horizontal tangent line. How about HTL for that? And then we'll work our vertical tangent lines or VTLs over here. So what's going on? Well, for the horizontal tangent line, if you remember back in the previous part of the notes, we said that that's going to occur when the numerator, which dy d theta serves as the numerator in this case, is equal to 0, as long as the denominator dx d theta, which I'm pretty sure we're going to be thinking about that in a little bit for our vertical tangent lines, is not 0. So we're going to have to keep an eye on both columns here. So let's take a look at when the numerator is 0. I am going to go ahead and distribute my cosine in to that second expression. So hopefully you see what I'm doing here. I'm just recopying cosine times sine, but I'm going to distribute this cosine in so that we have a better chance at solving this equation. And so this is what I'm left with. Cosine times sine plus cosine times sine. And all that's going to equal 0. Now, good news. We are able to solve this because all we need to do is factor out a cosine. Very easy. Tell me what's left. Well, that would be a sine plus 1 plus sine, or 2 sine plus 1. And we have now a form that will allow us to use the zero product property. In other words, we will set each of these individually equal to 0 and go about our merry business of solving this. You're really going to get a good trig workout. A lot of polar manipulation involves very strong foundational trigonometric skills. And if you don't think you're really good at those trig skills, you've got a great opportunity to improve them as you're working through polar equations in calculus. So we're going to solve this, which is going to give us pi over 2 and 3 pi over 2 whenever we're on the standard interval from 0 to 2 pi. And then as far as this equation is concerned, sine of theta equals -1 divided by 2. Some people are very wicked good at this and saying, boom, I know the answer. It's 7 pi over 6, 11 pi over 6, which is right. But to give a little bit more insight into why that's the case, basically, if you think about sine of theta being a half, that's going to give you a 1 over 2 opposite to hypotenuse ratio, which is only going to happen when you're at a 30-degree angle. That's a pi over 6 angle, my friends. And then if we love that mnemonic, all students take calculus, it's pretty clear to see that sine is negative here, and that's what's happening. And whoa, I almost lost my third quadrant there. That's going to be happening in quadrant 3 and 4. And the pi over 6 reference angle that so happily exists in quadrant 3 is 7 pi over 6, sorry. And the one that's in quadrant 4 is the 11 pi over 6. So wow, looks like there are 4 places where there's a horizontal tangent line. We'll see. And I want you to know, I know that the problem asks for where are the points, which does imply ordered pairs. For the purpose of this video, I'm only going to focus on finding the theta values. That's normally what I'm more interested in as a teacher, because to plug these in is just a little bit extra busy work that, we don't really have time for in the grand scheme of doing this very difficult problem. All right, guys, let's take a look at where our vertical tangent lines are. I'm going to do the same thing. I'm going to simplify that denominator as I work through it. Notice I have cosine times cosine to lead things off. That's a cosine squared. When negative sign distributes through, I'm going to have negative sign to the first and then a minus sign squared. And all of this gets set equal to 0. Now this one might be a little bit more challenging to solve. Anytime that you have sines and cosines dancing together, separated by pluses and minuses in an equation set equal to 0, we have our work cut out for us. So what we're going to have to do is think of another way to solve this. Wouldn't it be nice if every trig word was a sine? We would love that. Well, let's make it happen, because cosine squared, by way of a trig identity, the Pythagorean identity that is, can very easily be renamed as 1 minus sine squared. So now we might be in business. Now what I'm going to do at this point, I'm going to combine my like terms, but I notice that my leading coefficient for sine squared is going to be a -2. So as I combine like terms, with your permission, of course, I'm going to multiply each side by a -1 to kind of clean this up, to make it a little bit more conducive to our next step. So that +1 is actually a -1 there. So that's what I've got. And I'm hoping at this point you pay some special notice to this and realize that this trig equation acts just like this algebraic equation. It's a quadratic equation that is factorable. And sometimes we don't see that because we don't think of factoring trigonometric equations so often, but we can certainly do that. 2 sine squared can be broken apart into 2 sine times sine. The only way that we're going to get a 1 as our constant at the end is a pair of 1s multiplied together. Now we just got to play our signs correctly. To get a plus sign in the middle, if I put a plus here for the outside 2 sine theta, then my inside would be a -1 sine theta. I've got what I want. And now we can set these equal to 0 individually. Let's actually set it equal to 0 here. And now we're in business. Now we can solve these two equations and see what we've got. Sine of theta is 1/2, right? Let's move myself up there. Sine is -1. Okay, when are these happening? Well, the sine of theta is 1/2 whenever theta is pi/6 and 5 pi/6. Now, if you have to think about that a little bit, certainly pause the video, because I want you to work through some of these trig deficiencies that you may have, maybe you don't have, and get very comfortable with that. Let's see, sine of theta is -1. When is that going to happen? Well, the sine of theta is going to equal -1 whenever theta is 3 pi/2. Now, I'm getting that just from using the knowledge that we've all gained from the sine curve. And right there at that 3 pi/2 is where our -1 is reached. Now, it would be very easy for us to pat ourselves on the back and think we're done. But remember, it is so vitally important that you look to see if there is any common theta value to both solution sets. And one looks no farther than the 3 pi/2 to realize that we will cross him out, because that is going to be a place where there is neither a horizontal tangent line nor a vertical tangent line. It's a place on our curve where we could say that it's not smooth. It's probably going to look like a sharp point. Those are our 2 places for a VTL, 3 places for an HTL. Let's see if that's true. 3 horizontal tangents and 2 vertical tangents? Let's find out graphically. And we are back, right? And you can see our graph here. And maybe this is large enough. Hopefully it's not too terribly small. I can probably zoom a little bit. Maybe I'll zoom in. I'm going to give this a shot. I'm going to zoom box. How about that? I'll corner up here and maybe corner right about here. See if that helps just a little bit. Oh, it gave me a really bad sort of warped version of this, but you know what? I'm going to keep it like this because I think we're going to be able to see what's going on. Now, I said that there are 3 places where there's a horizontal tangent. Where are those places? Well, one of them is way up here at the top, and I believe that that's going to occur when we have a pi over 2 measure. Is that what we had in our findings earlier? And then we're going to have a couple of more places where there's a horizontal tangent line. One's right here, and then there's going to be another one right about there. So those would account for the 1, 2, 3 places where there's a vertical or horizontal, sorry, tangent line. Vertical tangents, one of them occurs right here, and the other one's probably somewhere over on this side, wouldn't you think? Right about there. Now the 3 pi over 2, if you're wondering, that's when I'm right there at the cusp of that heart, that point that makes our cardioid. And if you notice, the tangent line sort of disappears on us temporarily. And that's because the tangent line's having a hard time graphing when it has an undefined slope, or an indeterminate slope, I even should say. So that's why we're going to throw that point out, because we don't have conclusive evidence of what's going on, of it being a horizontal or a vertical tangent line. You're going to see a lot of these problems. I hope you get good at them. They're going to be wonderful opportunities for you to work on your trig. Hopefully this video helps out. We only have just another short video here to show you that's going to kind of close the doors on polar and calculus, and we're going to dive into some more advanced calculus that you can do with polar. Be sure to stick around. Thanks for joining.